In the last session, I had talked about two broad categories of solidification. That means, what are the two intrinsic solidification characteristics for different alloys, whether it is carbon steel, low alloy steel, or different stainless steels. So, basically the whole gamut of chemistry, whether for carbon steel or low alloy steels or even for stainless steels, it can be divided into two broad categories depending on their solidification characteristics. What are those? Basically, either they will be sticker type of grades, that means some of the grades, some of the chemistry ranges will show sticking tendency, will indicate sticking tendency during solidification, during continuous casting, and some of the grades will show depression characteristics. So, we call them depression grades, and where there is sticking we call those grades as sticker grades. So, you will find that these are the two broad categories into which the whole chemistry range can be distributed, that means can be subdivided. Either there will be sticking characteristics, so some of the grades will indicate the sticking tendency and the other grades will indicate depression tendency. Depression means the surface will have lot of undulations, surface is rough. So, then I had also mentioned the sticker grades for carbon steel or even low alloy steels. Normally they belong to either the carbon equivalent should be less than 0.6, that means the lower range of the carbon equivalent, or higher range, that means greater than 0.2. So, these two broad ranges will indicate sticking tendencies. So, now for the lower carbon equivalents I had mentioned, and also for ferritic type of stainless steel AISI 430, where the nickel equivalent divided by chromium equivalent is very low, those are the grades. You will find that it will indicate sticking because the solid shell is soft owing to its nature, that means it is a delta ferrite. During solidification, even slightly below solidification also delta ferrite will continue to be present. So, austenite transformation will start only quite low temperature, at quite low temperature, much below the solidification completion temperature. So, because of this delta ferrite, the shell is soft. Because it is soft, it cannot withstand the ferrostatic pressure. So, there will be tendency for sticking when it is in the mold. When the shell is coming out of the mold, so then it will indicate bulging tendency. So, sticking and bulging are basically owing or originating from the same same mechanism. So, either it is sticking within the mold or bulging below the mold. This tendency, this characteristics is typical for certain chemistry ranges, either very low or very high. So, I have talked about the very low chemistry ranges, carbon ranges, what happens, and then when the carbon equivalent is relatively high, more than 0.2, 0.25, 0.3 or maybe more, it may exceed, like ball bearing steel, where the carbon content, carbon equivalent is almost 1. So, in such type of steels, what you have is a very thin solid shell of austenite. Here it is austenitic solidification, particularly for carbon equivalent which is more than 0.5, or even when it is more than 0.2, initially it is delta ferrite, but then subsequently delta ferrite transforms to austenite at early stage of solidification itself. So, during solidification you have thin shell. Why it is thin? Because it is austenitic solidification. So, lot of microsegregation will be there, phosphorus will create a lot of microsegregation, sulfur will create microsegregation, all elements will create lot of microsegregation. Because of that, the solid shell is thin during solidification, the marshy zone is quite wide, quite deep. So, you have thin solid shell of austenite. So, since it is thin, it cannot withstand the ferrostatic stress. So, for carbon equivalent more than 0.2 and 310 type of stainless steel, which is a totally austenitic solidification, you will have thin solid shell of austenite, and it will again indicate sticking type of solidification characteristics. But what is going to happen for the depression grades? What are the depression grades? I have mentioned depression grades with coarse grains. I have also mentioned that if there is depression means the surface is rough, surface rough means there will be air gap between the solid shell surface and the mold surface. Because of this, the heat transfer is low, and consequently the grains, cast grains are coarse, dendrites are having coarse structure. So, what are those chemistries? For the carbon equivalent is around 0.1, or for stainless steel 304 type of grade, well, the nickel equivalent by chromium equivalent is around 0.55. So, for these chemistries you have depression tendency along with coarse grains. For the other chemistry ranges you have sticking tendencies with fine grains. Why fine grains? Because heat transfer is quite high, there is no air gap, so fine grains. So, these are the two broad categories of chemistry, and these are basically for the depression grades. These are basically the so-called, we call them so-called peritectic grades, because the chemistry lies at the beginning of the peritectic reaction, peritectic range of chemistry. So, these are the beginning, delta to rather delta plus liquid giving rise to austenite, delta ferrited liquid reacting and giving austenite. This peritectic reaction takes place for certain range of chemistry, and when the chemistry, typical chemistry is at the beginning of this peritectic range, that means around 0.1, and for stainless steel it is around 0.55 nickel equivalent by chromium equivalent. So, they are called so-called peritectic grades. They are belong at the beginning, the chemistry range is at the beginning of the peritectic range of chemistry. So, where the transformation from delta to gamma, it will take place in the critical brittle temperature zone corresponding to the solid fraction of 0.9 to 1, and in the temperature range between liquid impenetrable temperature RIT and the final solidification temperature, actual solidification temperature. So, when at that in this range towards the end of the solidification, this delta to gamma transformation is taking place, it causes additional shrinkage, and because of that there is relatively high amount of strain, because this shrinkage is adding up to the thermal shrinkage. So, total shrinkage is more for this type of chemistries, where delta to gamma is taking place, transformation is taking place around end of solidification, towards the end of solidification. So, there you have this depression grade, surface is rough, and you have coarse grains because of that. So, here what is happening? The solid shell is thick because microsegregation is relatively less, because this transformation is taking place, peritectic transformation is taking place towards the end of solidification. Initially there was delta, so the microsegregation was relatively less during early stage of solidification. Only towards the end this transformation is taking place. So, therefore, the microsegregation which takes place during solidification, so most of the time of the solidification we have only delta. So, the microsegregation is less, solid shell will be relatively thick, the marshy zone is relatively narrow, and towards the end of the solidification this delta is transforming to austenite. So, we have thick and strong solid shell of austenite. Because of this additional shrinkage of this, we have depression tendency. This I have tried to explain the two broad categories. Now, this also I have tried to explain that for the peritectic grade, so called when carbon equivalent is in 0.1, or for 304 stainless steel where nickel equivalent by chromium equivalent is around 0.55, because of the depression, this rough surface, there is air gap, relatively large air gap. So, heat transfer is less. So, we call it hot spot formation because of this, and because of this consequently the grains, cast grains are relatively coarse, whereas for the sticking type of characteristics, the grades which indicate sticking, there what is going to happen? The solid shell is trying to come in contact with the mold. So, there is sticking, that is why we call it sticking. So, the grains are relatively fine, but there is a sticking tendency. And if there is a sticking tendency between the solid shell and the mold, so we have lot of friction at this interface between the mold and the solid shell. Here this sticking tendency is not there because there is depression, rather here is a heat transfer is low. So, here you have, because of sticking, you have too much of friction. So, the mold slag should take care of this friction. Mold slag should be of characteristics which can resist this friction. So, friction is the issue for sticking type of grades, and for other type of grades where you have depression, heat transfer is the issue, because here heat transfer is coming down because of this gap formation. So, here the mold slag should control the heat transfer, should make it uniform throughout the mold periphery, so that you get a relatively less depression, relatively less this air gap formation, and relatively less coarse structure grains. So, that is why I have mentioned, based on these two broad categories, we have to design the continuous casting parameters. I will come into this after some time, but please remember these two basic characteristics, solidification characteristics, we have to keep in mind, and we have to design the casting parameters based on these observations. Then I have mentioned that earlier whatever I have shown was schematic, but when we measure the actual austenite grain size by simulating the continuous casting condition in Glibble, you can see that for 0.1% carbon, where I had mentioned surface is rough because of depression formation, and I had mentioned the cast grain size is expected to be coarse, which is validated by actual observations. 0.1% carbon cast grain size are relatively large compared to say 0.3% carbon, where cast grains are relatively finer. So, today I will talk about, I have earlier talked about one brittle temperature region which is around solidus, but when the liquid steel is getting cooled initially during solidification, and even beyond that, even lower than that, there will be certain other brittle temperature regions. Why we are bothered about the brittle temperature regions? Because since it is brittle, that means the shell is brittle, relatively brittle, so it cannot withstand any strain. Whatever strain will be generated during the course of solidification, and even lower than at temperatures lower than solidification, the strains should not be very high. Otherwise, when the shell is passing through these brittle temperature regions, there might be crack formation. And because of the crack formation, I have told you only about the brittle temperature region around solidus, but even lower than that there will also be certain brittle temperature regions. Let us try to understand. Now, when we are talking of brittle temperature region, what do we mean by brittle? Brittle, what is the measure of brittleness? Brittleness basically indicates that the reduction in area or the ductility of the solid shell is relatively less. Now, what is the quantitative figure? What figure we call it brittle and what figure we call it relatively less brittle and more ductile and more tough. So, normally this 50% reduction in area is taken as the boundary region between brittleness and toughness. So, if the reduction area is less than 50% at any temperature region, if the solid shell has a reduction in area, that means the ductility or reduction in area, it can be measured. This ductility and reduction area can be measured. So, if it is less than 50%, that means when you are deforming that particular shell, how much area is reduced, how much cross section area is reduced. From that you can actually find out the ratio, the percentage of reduction in area. So, if the reduction in area at any particular temperature region is less than 50%, then we call that in that particular region the material is brittle. And if it is more than 50%, so 70%, 80%, 90%, then we call that particular temperature region is ductile. That means the shell, solid shell will behave in a ductile region, ductile manner. And why ductile is good? Because it can withstand some deformation, it can withstand lot of strain. Even if there is strain, it can accommodate that by getting deformed. So, if the deformation of the shell is there, that means the reduction in area is more, so it can deform more, it can withstand higher amount of strain. Because of that, crack formation will be less. So, whenever the reduction in area of the solid shell is less than 50%, we call it brittle. So, at whatever temperature reduction area is less than 50, we call it, those temperature regions we call it brittle temperature region. Now, the solidifying shell, it is coming during solidification, it is from liquid it is becoming solid, and from solid again it is cooling down. So, there is a temperature loss from the liquid state till we come down to the solid and almost low temperature region. So, this solidifying shell during cooling, they are basically undergoing 3 brittle zones. I have talked about one brittle zone only. What is that brittle zone I have talked about? Is around and slightly below actual solidus temperature. So, I have mentioned in quite details that this actual solidus slightly above that and slightly below that is really brittle, because this reduction area is 0 at solidus temperature, and at temperature slightly lower than that it is only increasing, but still it is less than 50%. So, till about 50 degrees centigrade below solidification is completed, we have brittle temperature region. At solidus, at actual solidus, reduction area is 0, because nil ductility temperature we call it. So, that means the reduction area will be 0, it is still brittle. So, as the temperature is coming down from that, from the solidus, as you are cooling, so till about 50 degrees centigrade ductility is low, it is less than 50% reduction area. So, therefore, around and below actual solidus, below means till 50 degrees centigrade below the actual solidus is the brittle temperature region. I have talked about this. Then what is going to happen? Why are we bothered about this area? Because if there is some stress in this zone, if there is some strain in this temperature region, so there will be intercolumnar crack. I have mentioned that the structure of the solid shell is columnar. So, between the two columnar zones we have weak area, we have mode of segregation in those areas. So, those are relatively weak. So, we call it that in those intercolumnar areas there will be crack formation. So, these intercolumnar cracks will form at the relatively high temperature around solidus. So, we have to be careful about this temperature region. Next, when it is getting cool, this temperature is, it depends of course on the chemistry, but it can be 1450, it can be 1400, it can be 1350, it can be 1300, depends on if the carbon equivalent increases or the nickel equivalent by chromium equivalent increases, this solidus temperature also decreases for the different chemistries. So, what I am talking is around solidus and about less than 50 degrees centigrade of the solidus. This is the high temperature brittle zone, first high temperature brittle zone. Next, when the solid shell after solidification has taken place, solid shell is coming down in temperature, that is it is becoming less and less hot, it is becoming more and more cold. So, what is going to happen? Say around 1200 degrees centigrade, about 1250 degrees centigrade is okay, toughness is relatively high, toughness is reduction area is more than 50%. So, it is good, but when we come to this particular temperature region about 1000 to 1100 degrees centigrade, what is going to happen? Here phosphorus, sulfur, oxygen, these are all, some of them are surface active, they are going to segregate to the intergranular austenite. That means, whatever austenite grains have formed at this temperature region, you have only austenite grains. Whatever delta ferrite was there, grains of delta ferrite, they have got transformed to austenite either during solidification or for very low carbon chemistries or very low nickel equivalent by chromium equivalent stainless grades, they get transformed at lower temperature during cooling at temperatures lower than solidification. During solidification it is delta ferrite but very low carbon, but when it is getting cooled at lower temperature, this delta to gamma transformation in solid state will take place. So, around this temperature 1000 to 1100 it is only austenite. So, what is going to happen? This segregation of phosphorus, sulfur, oxygen along intergranular, that means the austenite grain boundaries, if they segregate, the grain boundary becomes relatively weak and there is a possibility of crack formation along these grain boundaries. So, here it is intercolumnar, that means between the columns, between the I have told you about the cast structure, the coarse cast structure, there we have lot of columns, and intercolumnar areas you have relatively weak areas because of those areas have too much of segregation. So, intercolumnar cracks can form. Here intergranular austenites are forming in solid state. Here it was columnar zones during solidification. So, that was relatively high temperature, but this particular intergranular austenite problem is around 1000 to 1100 degrees centigrade. Now, when temperature is coming down to less than 1000, again the reduction area is relatively more. So, that is not a brittle area, that is a relatively ductile area. But when the temperature is coming to less than 700 degrees centigrade, then what is going to happen? Then there is a problem of precipitation of nitrides of aluminum, niobium, vanadium. Niobium, vanadium, these are microalloys, niobium, vanadium. So, in microalloy steels you have these microalloying elements, and aluminum you can have in any aluminum kiln steel. So, the problem is the formation of nitrides of aluminum or nitrides of niobium, nitrides of vanadium, they can form along the grain boundaries of austenite around this temperature. And as I have told, certain grades of steel, particularly those which are of depression type, that means when the carbon content is around 0.1, or the nickel equivalent by chromium equivalent is around 0.55. Those grades are prone to depression. Depression means the grains are relatively coarse. So, if the grains are coarse, what is going to happen? The grain boundary areas are relatively less. If you have coarse grains, the grain boundary areas are relatively less in area. If you have finer grains, grain boundary areas are quite numerous and quite relatively high in area. So, this formation of this aluminum nitride, niobium nitride, vanadium nitride, if you have coarse grains, the grain boundary areas get relatively more dense because of this formation of these nitrides. And if you have fine grains, the grain boundary areas are quite large. So, the density of these nitrides will be relatively less in fine grain situation. But for coarse austenite grain situation, you have relatively higher density of this nitrides along the coarse austenite grains. So, again this particular temperature, because of this formation of these nitrides at the coarse austenite grains, certain chemistries are relatively more prone to brittleness, around the so called peritectic grades, around 0.1% carbon, or the 304 stainless steel, which has a nickel equivalent and ratio of nickel equivalent by chromium equivalent around 0.55. So, those chemistries are prone to this brittleness around 600 to 700 degrees centigrade. So, you have to be careful that during continuous casting, the shell should not come to this temperature region. You have to avoid this temperature region. How you can avoid it? You can cool it in a particular cooling rate, so that you do not allow the temperature to come along this temperature region when you are actually cooling it. Here strain rate is also important, but certain strain rate, whether it is low or high, these brittle temperature regions will indicate relatively more brittleness, more crack formation. But right now I am talking only about the temperature regions. So, what I have mentioned, there are 3 brittle temperature regions. Relatively high temperature, that means just around solidus, we have one brittle temperature region which is around solidus. Then as we are cooling the steel around 1000 to 1100, again there will be brittle temperature region, which is because of segregation of phosphorus, sulfur, oxygen along intergranular austenite, along the grain boundaries of austenite. Now, as we are still coming down to at low temperature, that means during cooling, because of secondary cooling, the surface temperature and the interior temperature is also coming down slowly. So, we have to avoid another temperature region 600 to 700, because what happens at those temperature regions, the nitrides are going to form along the coarse austenite grains of austenite. So, we do not allow them to form. That means, if we cool the continuous cast product in this temperature region relatively faster, so what is going to happen? These nitrides, they do not get adequate time to form at the coarse austenite grain boundaries. So, we have to cool them relatively faster. We do not give sufficient time for the formation of the nitrides of aluminum, niobium or vanadium. So, this is the secret of avoiding the brittleness around this temperature. We cool relatively faster, so that this temperature region you can avoid. The secondary cooling you can design in such a way, so that this particular temperature you can avoid for those chemistry, the grades having around 0.1% carbon or 304 stainless steel, where nickel equivalent by chromium equivalent is around 0.55. So, what I was telling was, depending on the characteristics of the grades, you can design your continuous casting parameters. What are the continuous casting parameters? You can design what will be the heat transfer in the mold. How do you control it? You can control it by using particular characteristics powder. That means the powder will finally melt and give you mold slag. So, what is the viscosity of the mold slag? What is the solidification temperature of the mold slag? This will give us a particular heat transfer. This will give us how to resist the friction, because as I have mentioned, for certain grades like those are sticker type of grades, very low carbon or very high carbon, there is a problem of sticking, there is a tendency of sticking. So, the mold slag must resist this sticking. Mold slag should have sufficient characteristics to resist this sticking tendency. So, the mold powder characteristics we have to design based on whether it is a sticker grade or it is a depression type of grade. So, this is one. Number 2, the secondary cooling, that means when the shell has or the strand has come out of the mold. So, then you use secondary cooling. How much secondary cooling, how much water you will use, how much mist you will use, whether it is a mist formation. Mist formation incidentally is relatively, you can better control the heat transfer during secondary cooling. So, how much do you use, what is the distribution of the cooling as you are coming down from the mold till the continuous casting is over at the final stage of cooling. So, these are dictated by the type of steel, what is their characteristics. So, mold cooling, secondary cooling, casting speed, the oscillation characteristics I had mentioned earlier, for sticker type of grades, because oscillation is basically done for what? Done to avoid sticking. So, for those grades you use relatively larger amplitude and lesser amount of frequency of oscillation. But for the other type of grades, the depression type of grades, there is a sticking is not a problem there. There is a problem is surface roughness. So, we do not want surface roughness. So, what do you want? The frequency should be relatively more and the oscillation should be relatively less, just the reverse of the sticker type of grades. So, the mold oscillation characteristics should be different for these two types of grades. Mold powder should be different for the two types of grades. Secondary cooling characteristics should be different, how much of water, how much of mist will be used, what is the distribution, all these will depend on what type of grade we are using. The whole idea is to avoid formation of crack. So, the chemistry will dictate the solidification characteristics, will give us what is the solidification characteristics, whether it is a sticker grade or depression grade, and depending on these two broad categories we have to design our continuous casting parameters. So, I am mentioning again and again continuous casting parameters like extent of primary cooling, which is dictated by the powder characteristics, or whether it should take care of the friction, because if you have sticking grade, that means the friction is a problem. So, the powder characteristic should be such that friction is taken care of for sticker type of grades, but for the depression type of grades sticking is not a problem, friction is not a problem, not an issue. There the issue is heat transfer in the mold. So, there the powder characteristics have to be different, number 1. Number 2, mold oscillation characteristics again have to be different because of these two types of grades. Also, the secondary cooling characteristics, that means how much of water will be used, what is the intensity of cooling, what is the distribution of cooling from top of the secondary cooling zone to the bottom of the secondary cooling zone. All these will depend on the type of grates, the chemistry of the grates. Now, I have mentioned what should be done to prevent the cracks, but in spite of all our efforts, in spite of lot of care whatever we take, if we do not take care, there will be definitely a lot of crack formation. So, the quality is bad, but even if we do lot of, even if we do casting with lot of care, that means we take care during continuous casting, there is a possibility of crack formation, because as I have mentioned, there are certain brittle temperature regions when continuous casting is taking place during solidification, end of solidification at that temperature region, and also when the cooling is taking place, there are certain brittle temperature regions. So, we have to avoid crack formation during those regions.